Hello everyone. So in this video, we're going to talk about surface area and volume. And this is very straightforward in the sense that we are no longer going to be looking at just like flat objects. And what I mean by flat objects would be something like a basic square here. We know a square, the area would equal, if I label the sides length times width, or length and width, the area would be length times width. This is a flat object, okay? When we think about surface area or volume, what we're really trying to consider, what we're really trying to find, let's just write it like this. For surface area, what we're trying to find is the sum total of the areas of each face. Meaning, if I, instead of having a square, all right, now we're talking about a three-dimensional object, which would be a cube. So what we're concerned with now is figuring out or painting, if you will, each individual side. So like, this would be the right side, then the left side, the bottom, the back, the top, and finally the front. All right. Volume, on the other hand, you could think of as like the amount of space contained inside of the object. Sorry, let's write this a little cleaner here. Of the object. So it's kind of like, all right, well, if I have this cube, right, and I wanted to start filling it up with water. Oh man, I thought I had the blue marker out. There we go. If I wanted to start filling it up with water, how much space will I occupy within this shape? So those are the two big differences here. So you're going to have to excuse me because I am not an artist. So I am just going to be copying and pasting some pictures from your textbook into this video or into our notes. So the way that we want to approach surface area is to once again think about, okay, like what does this three-dimensional object look like if I were to kind of create like a flat dimension of it? So like, for example here, here's a nice rectangle, okay? In fact, let me redraw it down here. All right, now, if we want to find the surface area, we're going to have to create a three-dimensional object. Okay? And notice here that we have some sides are the same. In other words, and I'm going to try my best here to say, okay, we got the front and we got the back. All right, now those two sides are going to be the exact same. So what I can do over here to the right-hand side is kind of just label this as like front and back. And I know the area of this would just be, let's call it length times width. All right. So because I have front and back, I have two of these. So the area would be 2 times L times W. All right. So that would be like I said, front and back. So let's go ahead. Let's try to label this length and width. All right. Now, using a highlighter here, we have the right side, we have the top, we have the bottom, and then we have this far left side here. All right. Now, those are going to be paired up as well. So like, for example, let's just do the sides here. All right. Oops, wrong marker. Here we go. So if I were to do this again, notice here I have, and I'm going to label this the sides, okay? But this is still going to be basically the same exact dimensions, all right? This is length. Actually, since this is a rectangle, let's make this D for depth. So this is going to be D times W, all right? And since I have two sides, the area of that will be 2 times W times D. All right. And finally, we're going to have the top and we're going to have the bottom. So here's our top and then here's our bottom. All right. So the top / bottom will have the following dimensions. So it's going to be the top. So let's see, that's going to be L times D. So L times D, and the area would equal 2 of them. All right. And remember when I said earlier about the surface area is the sum total of all these faces. So the sum total for the surface area of our box will be area equals 2 times LW plus 2 times WD plus 2 times LD. Now, within your book, all right, they have a much better way of explaining this with actual dimensions, okay? But I'm going to go ahead and just copy and paste it right now just to show you what this looks like in your text, okay? So, give me 1 second here. So, here is the box that they were referring to. There we go. And you can see here how they kind of broke everything up. So what I'm going to try to do is I'm going to try to color code everything for you. So here's the top, here's the bottom, and that's going to be represented right here. Now you have this left back side and then the far right side. They're going to be right here and right here respectively. And you can already see how this is getting messy, but we'll just deal with it. So then we have the front and the back. And they are right here. Okay? And then what your book did, or what it does for us, is it kind of breaks down, here. How do we actually look at these in terms of summing up all the shapes? So that's going to be right here. All right, so for example here, we have the top and bottom. So that's right here. Then we have the sides. So I think I made the sides this color. So here are our sides. And then finally, the front and back. And that's this color right here. All right. So the easiest way to do this is to kind of think of it in terms of like just separating on all these shapes and finding out the individual areas of each face and then bringing them all together. Now, your book does a really good job, and it kind of gives you like a game plan right here. So this is figure 19. And as you can see here, they have the shape, and then they have the shape, what it would look like when it's completely separated out, all right? And that's going to really help you out when it comes to taking a 3-dimensional object and then creating a 2-dimensional object in its place. Now, the one shape that is very easy to understand once you see it is the surface area for a cylinder. So here's my best drawing of a cylinder. So it has like a radius or a circle up top. Then it comes down. And it has another circle on the bottom. So it's a can. If you think of a can, it's exactly what it is. All cylinders have a height. And they also have a radius. Now, if you wanted to find the surface area for a cylinder, all right, and like I said, if you think of a can, or better yet, if you just take a sheet of paper and create a cylinder, you can already see that the top and the bottom all right, are just circles. That's all they are. So you got a top and you got a bottom. All right. And then, like I said, if you took that piece of paper and created a cylinder, the can part or the axial part is nothing more than a rectangle. However, this is where it can get a little weird if you think about it. This is a rectangle where the length and the width are actually a little bit different than what you would think. The length or the height of the can is still going to be the same. All right. But it's this width part. It's right here. I'm going to highlight it in green. It's this part where we have to remember that since this is a circle, that length is actually the circumference of a circle. All right. So when we want to find the surface area for a cylinder, all right, what we have to do is we have to take the top plus the bottom and then plus and this is what we call it, a curved surface, where the curved surface is this rectangle looking thing. So, area of a circle. Sorry, let me just finish this real quick. So the area of the top circle, pi r squared. Area of the bottom circle, pi r squared. And then the curved surface, remember, it's a rectangle, so it's still going to be the long side times the height, but in this case, it's going to be their circumference, 2 pi r times h. And if you look here, we have like terms. So at the end of the day, the surface area for a cylinder is 2 times pi times r squared plus 2 pi rh. So if we wanted to just find the surface area for the cylinder, all right, and here's our cylinder right here. The height is 10 and the radius is, we'll call it 5, and this is 10 feet. So this is a pretty big, I don't know, silo, if you will. All right. The surface area is going to be 2 times pi times r. Now, r in this case is going to be 5 to the second power plus 2 pi times 5 times 10. Now, the next thing I'm going to show you here is very, very important. Whenever we use pi, we can have 2 different answers. Now, what I mean by different is they're not going to be incorrect, all right? Not like one's correct and the other's incorrect. We get 2 types. The first type is called an approximation. All right? Whenever we talk about an approximate answer, what we're really saying is go ahead and use 3.14 for pi. So if you look at our formula above, our surface area is going to be 2 times 3.14 times 5 to the second plus 2 times 3.14 times 5 times 10. And I'm going to pause the video and go ahead and use my calculator here. All right, so here's our calculator. We're just going to, like I said, we're going to use this to help us. So we got 2 times 3.14 times 5 to the second is 25 plus 2 times 3.14 times 5 times 10. So we come up with 471 square feet. All right. This is an approximate answer, though. The other type of answer that we could get is what we call an exact answer. Now, exact answers do not approximate pi. In other words, we're going to rewrite our formula above. So we got our surface area equals 2, but instead of writing 3.14, I'm going to rewrite it as pi. And I simplify everything except I do not worry about pi. In other words, our surface area here will be 5 to the second, which is 25, times 2 is 50, so this will be 50 pi, plus 2 times 5 is 10, 10 times 10 is 100, so this is 100 pi, and then I would combine these two answers together to give me 150 pi square feet. All right. So, like I said, whenever we use pi, we get two answers. You got to read the directions to determine which one do they want. Okay. If they want an approximate answer, use 3.14. If they want an exact answer, include pi. Do not multiply the pi. Just carry it along for the ride. The last thing that I would like to talk about is going to be the units. Notice the units are square feet. And this will be like the last big thing of the day. Well, last big thing of this part of this section. How about that? Anytime you are finding area, the units will always be squared. So like, for example, you could have like square feet. Another way to write that is just SQ with a dot feet, or meters squared, or inches squared, or square centimeters. It's always squared. And the reason, because you're multiplying units. If you go back in the day, if you think about x times x, well, the bases are the same. So you add the exponents together to give you x squared. Well, this is the same thing as feet times feet. If you think about this, the ft, that's simply raised to the first power. And since the bases are the same, you add those exponents together. And that's why we get that squared feet thing. Now, the last thing we're going to talk about is going to be the second half of this video, which all deals with volume. So what's nice about volume is you already have a pretty firm understanding of what's happening. All right. First thing, we're going to start off with a nice square. Now, if we have a square and we turn it into a three-dimensional object, all right, we call this a cube. Now, if you have a square, remember, a square has all the same sides, which means a cube has all the same lengths, widths, and heights. So the volume of a cube is length times width times height. Now, I'm sure some of us out there have heard of this phrase before. All right, I'm going to show you where it comes from. Whenever you go to a doctor or something like that, and you get a shot, or you watch a TV show where they're talking about giving somebody a shot, they always say, "Can I have like 30 cc's?" Right? That cc thing. Well, here's where the cc actually comes from. All right. So I'm going to try my best to draw a really good cube. In fact, let me see if this program that I'm using actually has a cube in it. All right, so the program didn't have a cube, but I drew one anyways to the best of my ability. So this whole CC thing, well, here's where it comes from. If I have a cube where one side is 1 centimeter, that means all the other sides are 1 centimeter as well. All right. According to the formula for the volume of a cube, it's length times width times height. So this is going to be 1 centimeter times 1 centimeter times 1 centimeter. We know 1 times 1 times 1 is 1. However, centimeter, just like when I was talking about the units for area, this is going to be centimeters raised to like that first power. So when the bases are the same, you add all the exponents together. So this will be centimeter to the third power, or as we always hear it, cubic, the cube we just drew, cubic centimeters. And that's where you get the phrase or the acronym CC from. All right. So what's nice, like I said, about volume is you already have a really good understanding on how to do this. We're just going to marry the idea of the area of a base of a shape, and then we're going to extend it into some sort of space. So like, for example, if we had this shape right here, all right, which is a circle. Wow. I have no idea what just happened, but it just created a perfect circle. I know the area of this is going to be pi r squared. Okay? But then if I take this and I extend it up in the air, I think I know. Here's what happened. Automatic shapes. I want to turn that off. There we go. See, I was trying to do something early, but anyways. If I were to take this circle and now give it some sort of dimension, okay, where that's the height, what I just found is no longer the area, but the volume. So I took a circle and I found the area of the base. So the volume equals the area of the base multiplied by the height. So the area of the base, well, that would be like the circle. And then I just multiplied it by the height. And that's it. So the volume of a cylinder is V equals pi r squared times the height of the cylinder, h. Very, very straightforward. The thing we have to remember would be the units for all volumes are always raised to the third power. All right, because you're dealing with space now. You're multiplying 3 numbers together. All right, so it would be like feet cubed or cubic feet, meters cubed, inches cubed, whatever. Just remember, it's to the third power. All right, so we have the volume of a cylinder. Now let's look at the volume of a triangular prism. So a triangular prism is exactly what it sounds like. It's a triangle. But now if you make this into a 3-dimensional object, now you have what we call a triangular prism. Again, the volume is going to be equal to the area of the base times the height. So the area of the base is right here. I'm gonna color code this in purple. So that's going to be 1/2 base times height, because that's what a triangle is, right? Base times height. So that's going to be B times H. And then we have to multiply this by the height again, which is going to be this right here. Actually, you know what? Instead of using H, let's use a different letter. We'll use W for width. And that's going to be this whole thing right here. So it's going to be all of that. All right. Finally, we have a couple more formulas that we're going to go over. We have one of my favorite shapes, which is a pyramid. I am not going to try to draw this. I'm going to just use your book, all right, because they do a great job at explaining all the different kinds of forms that a pyramid could take. So here it is right here. All right. But what's nice about this, the volume of a pyramid is going to be 1/3 times the area of the base times the height. Now, the only thing you got to be careful of, all right, is the height is going to be capital H, all right? So the height of it would be like, if I can try to draw this on this green one, it's going to be right here. So put a dot at C and bring it straight down. That's going to be its height right there. Sometimes you have a cone. Once again, I'm going to use your book because they do such a good job at drawing a cube. Or I mean, what did I call it? A cone? And I'm not even going to mess with it. Are you going to let me copy and paste this? There we go. All right, so here we can see the volume once again. Oops. It's going to be the area of the base multiplied by H. But in this case, the base is right here. It's a circle. So we know the area of the circle is going to be pi r squared. Oops. Times H. And finally, we have the area of a sphere. I'm sorry, did I say area? I'm in volume. We're in volume land. So the volume of a sphere, which is nothing more than just a ball where it's in 3 dimensions now. And the volume of a sphere is volume equals 4/3 pi r cubed, where r is going to be the radius. So the hardest part about this section is just knowing what formula to use and when to use it. All right. But we do have to be careful, because a lot of people, unfortunately, try to lie to you all the time. Now, what do I mean by that? All right. So here's a question I'm going to ask. Does the volume double? All right. So I have two of the same shape. All right. So the first one is going to be a cube, where all the sides are 1 centimeter. Now, if we were to double the size of this cube, that means the length, the width, and the height would all be times 2. So now we have this shape here. So it looks very similar to what we're used to, okay? But what happens to the volume? Does it double? So if you double the length, or double the height, or double the width, does the volume double? And the answer is No. It actually goes up dramatically. Let me explain to you why. In the first example, the volume of that cube is 1 centimeter cubed. Very straightforward. However, 2 times 2 times 2 for the second example is 8. So our volume increased 8 times. So just because the shape faces get bigger, the volume dramatically goes up. So with all that being said, that's going to be it for this video. Just remember, be careful when you are using formulas. You just want to make sure you make the proper substitutions and remember the units. See you in the next one.